Okay, folks, we are going to pick up where we left off on the notes page yesterday. We had covered everything except, I believe, the last two examples on the back of the notes page. Before we start there, we're just going to do a brief review of what we discussed yesterday. Yesterday we talked about simplifying logarithms and what you would need to do if you were going to combine logarithms together. If you remember yesterday, we said in order to combine two logarithms together, two requirements have to be met. First, the two logarithms have to have the exact same base. Secondly, those two logarithms both have to have a lead coefficient of 1. Okay, something else that we'll need to make sure that we remember for today is that you can take any number, any constant number, and you can disguise that number so that it looks like a logarithm. For example, if you had the number 13 and you wanted to make that look like a logarithm, essentially you could choose any number that you like for the base of the logarithm and just make sure that the argument's base for that logarithm matched so that those are exactly the same, and then you would take the number 13 and make that the exponent on the logarithm's argument. That is this property right here that we discussed yesterday. Okay, that would all really just simplify down to the number 13. Okay, so the one property that we did not get to look at yesterday was the property called the one-to-one property. And I want you to draw a little arrow there and make a note to yourself that this is the one property that only applies to equations. Okay, this is the one that there has to be an equal sign, it has to be an equation for you to execute the one-to-one property. Now, the way this property works is if you condense everything on the left side of the equation so that there is a single logarithm, and you condense everything on the right side of the equation so there is a single logarithm, provided that those two logarithms have the exact same base and have lead coefficients of 1, you are permitted to take those logarithms along with their bases, cross those off, and leave behind simply their arguments set equal to each other. I'll give you an example of this to fill in underneath the one-to-one property on your notes. Let's say that you had log base 4 of 81 on the left side of the equation, and on the right side you had log base 4 of 3x. Since you have one and only one logarithm on the left side of the equation that has a base of 4 and a lead coefficient of 1, and you have one and only one logarithm on the right side of the equation which also has a base of 4 and a lead coefficient of 1, you are permitted to cross off each of those logs. This is why this is called the one-to-one property. There has to be one logarithm on each side of the equation. That would leave behind 81 equals 3x, just their arguments, and then you would continue solving that equation for x, and you would get the answer x equals 27. Okay, once again, this only applies to equations. Now there is one important characteristic of logarithms that you'd want to make sure that you are aware of. And that is that when you have a logarithm, its argument has to be a positive number. If you were to try on your calculator right now to just type that log button that we all know has a base of 10 and make the argument maybe -2, you would end up getting an error on your calculator. In fact, even if the logarithm's argument were 0, you would still get an error. So one restriction on all logarithms is that the argument has to be a number that's greater than 0. Okay? Now this is important with the equations because when you're solving your equations, we'll need to do a little checking just to kind of make sure that our answer, when plugged back into the original equation, would not cause any of the logarithm's arguments to become either 0 or negative. Okay, so I'm going to have you go ahead and flip to the back of the notes page here. We're going to start with example 4, and you'll notice what I was just referencing there in regards to the domain restrictions that's noted here at the end. It says the arguments in the original logarithms have to be positive. Okay? So immediately, as soon as you notice that your problem is in fact an equation, you should think of the one-to-one property. And the very name of this property tells you the situation that you need to make sure is created in the equation. And that is that you have one and only one logarithm on the left side of the equation, and then also one and only one logarithm on the right side of the equation. As you look at example 4a, you'll notice that we already have that situation in the problem. There is only one log on the left and one log on the right. Both of those logarithms have to have the exact same base, which in this problem, they both have a base of 2, and the two logarithms have to have lead coefficients of 1, which is also the case. So according to the one-to-one property, we are permitted to cross off the log and its base, leaving behind only the arguments that are now equal to each other. What we would then do is we would take this equation and we would solve this equation for x. Now, what you're going to find in a lot of these problems, not all of them, but a lot of them, once you get to this point, you might notice that you're going to have an x that's squared. Okay, we've discussed this before. We know that this is a quadratic equation, and we've discussed many different ways to solve quadratic equations. We could factor, we can graph. I have given all of you the Quadratic Formula program already on your calculator. And since our focus in this chapter is going to be on the logarithm properties, I'm going to permit you to use the Quadratic Formula program on your calculator as a way of solving these quadratic equations. Now, one thing that is true, if you're going to do the quadratic formula, you would have to take everything in the equation and make sure it's all moved to one side. And of course, we'd want to write that so that it's in descending order. Okay. Then, when we do the quadratic formula, we would identify our value of a, b, and c. And then on your calculator, what you're going to press that black program key in the center. And you're going to notice that if you have other programs, it will alphabetize all of them there in this list. You're going to want to pick the program titled Quad. When you select that, you will press enter and it'll immediately start you with the program. It should come up with an A, equals, and a question mark. That's where you're going to type on your calculator that for this problem, the A has a value of 1, and you'll press enter. Okay. It'll continue on to ask you for the value of B, which you'll type -7, and then the value of C, you'll type 12. Okay. It should then give you off to the side the two values for which x would equal for this particular quadratic equation. I'm seeing on my calculator x equals 4, x equals 3. Okay, here's where, before you circle these two answers, you have to make sure that you are checking for domain restrictions. So you're going to go all the way back up to the original problem and just verify that if you were to take a value of +4 and substitute it back into the equation for the x's, would that cause either of those two logarithms arguments to become either 0 or negative? If the answer is yes, then we should throw the number 4 out. It's not actually an answer to this problem. Now you can see that if you were to plug 4 back in to either of those two logarithms arguments, it's not going to make the argument 0 or negative. So 4 is definitely an answer that we would want to circle and keep. Okay. Same would be true if we attempted to substitute the 3 in to each of those x's. The argument still would be positive. Okay. So we're going to keep both of those as answers for the x. All right, so we're going to go ahead and try the second problem. This one is definitely a little bit more complicated. Okay, we immediately notice that this problem is also an equation. See the equal sign there. So what we're going to do is we're going to say, okay, we need to make sure that we are doing the one-to-one property. And according to the one-to-one property, we use our equal sign kind of as our barrier here in the middle. We need to have one logarithm on each side of the equation. Now, the left side of the equation, the right side of the equation rather, we already have one logarithm there. So we don't need to do anything to the right side of the equation. However, the left side of the equation, you can see there are two logarithms. So we learned yesterday how to take two logarithms and combine them together into a single logarithm. Now, according to the front of the notes page here, I'm just going to flip back here real quick. In order to combine two logs together, they A, have to have the same base, B, they have to have a lead coefficient of 1. Well, these two logarithms have the exact same base. It's the letter A, but I notice that the first logarithm does not have a lead coefficient of 1. It is a 2. So again, I'm just going to scroll back. Yesterday, we did discuss one property. Okay, that property was called the power property, and according to the power property, it said that's fine if you have a number in front of a logarithm. You are permitted to take that number and pull it up so that it becomes the exponent on the argument. That's exactly what we would do here in this situation. We're going to pull that 2 so that that becomes the exponent on that logarithm's argument, so that now the lead coefficient for both of those logarithms are 1s. Okay, so our next step would be to try to now combine these two logarithms together. Because again, the one-to-one property says one logarithm has to be on the entire left side of the equation and one logarithm on the right side. Now, if you look closely, what we're doing with these two logarithms, we are taking the two logarithms and we are adding those two logarithms together. So again, yesterday we learned that if you add two logarithms, you take their arguments and you would multiply their arguments together. So we would multiply x squared times 2, and that would make the new argument 2x squared. Now at this point, since we have one logarithm on the left and one logarithm on the right, we would take each of the logarithms and their bases, and we are permitted to cross those off based on the one-to-one property. That leaves behind only the logarithm's arguments that are now equal to each other. Now, if this equation was not a quadratic, if it did not have an x squared in it, you would continue solving this like you would a normal basic algebra equation, gathering all the x's on one side and the other constants on the other side. But since this problem, similar to the previous one, is a quadratic because there is an x squared, we're going to move everything all to one side of the equation, set it equal to 0. And again, you can pull up that quad program on your calculator, that black button, select the quad program, hit enter, and it's going to ask you again, what's the value of A, what's the value of B, and what is the value of C. Okay. Now when you run the quad program with an A value of 2, a B value of -5, and a C value of -3, the screen is going to tell you that your two answers are +3 and -12. Now, I should mention this. Sometimes these quad programs get corrupted for some reason. If you are running the quad program and you are not getting these answers that you're seeing me write down, make sure to mention that to me in class and I will give you the quad program again on your calculator. I'm not sure why sometimes the program gets corrupted, but let me know and we can fix that easily. Okay, so here's where, before we circle our answer, we need to make sure that we are checking them. And if you notice, you're going to always see in the directions, it's going to mention for these equations that we should check our answer. Now, where you're checking it is you're always checking it in the original equation before you've combined anything, manipulated anything, moved anything. Okay, so you want to go all the way back to the beginning where we still had that logarithm that had the 2 in front. Okay? You're going to ask yourself, if you took the number 3 and you were to substitute that in for either of those two x's that are in the logarithm's arguments, would that 3 plugged in cause any of those logarithm's arguments to be either 0 or negative? And the answer is no, that would not. So that means we're going to keep the number 3 definitely as an answer. Now let's check negative 1/2. If we plugged negative 1/2 in for, say, this x, I'll work this out off to the side. If we plug negative 1/2 in for the x all the way in that logarithm to the right, I think 5 times negative 1/2 is negative 2.5 plus 3 really makes that logarithm's argument a positive 0.5. So far, negative 1/2 plugged into that far right logarithm's argument, that checks out okay. The argument would still be positive. However, if we were to plug negative 1/2 into this other logarithm's argument there on the left, this is before the 2's pulled up, a negative 1/2 plugged in there means that that argument is a negative 1/2. So we cannot have logarithm's arguments be 0 or negative. So for that reason, we're going to toss negative 1/2 as being a possibility for an answer. The only answer for this problem is positive 3. Okay. Now, these equation problems can look really different. Okay. This is just a sampling of how a couple of them can look. So what I'd like to do with you here real quick is your homework assignment is going to be the same worksheet from yesterday. You only had certain problems to do yesterday. We're going to do the other problems that you did not have to do, which would be problems 4 and 5, 7 and 8, number 10, I believe, 12, and then 14 through 17. Now, some of those are review from yesterday, but the 3 that are on the back are the ones that are equations, like what we've done today. And I'd like to just get you started with problem number 15, because these ones on the back, they look a little bit different than the 2 that we did on the notes today. So let's just take a look at number 15 together here. I'm just going to jot it down real quick. I want to make sure that we're always using the one-to-one property when we are doing these logarithm equations. Okay. So if we're doing the one-to-one property, that says you should have one and only one logarithm on each side of the equation. And if you look at number 15, you'll notice that it actually has 2 logarithms on the left, and there are really no logarithms at all on the right side. It will be easiest if with these equations, you're not moving things over to the other side of the equation. So I would leave things exactly where they are at in their original equation. So what we would want to do is we would want to take the 2 logarithms that we have on the left side, and we would want to combine those 2 logarithms together so that they are one logarithm, similar to what we did here in example B on the notes page when we had 2 logarithms on the left. Now, once again, they have to have the same base, which they do here, and they have to have lead coefficients of 1, which they do. Okay, so we just want to pay special attention to whether this is asking us to add or subtract the 2 logarithms. So we know when we add, we are multiplying their arguments. When we subtract, we are dividing. Now, in this particular example, we are adding these logarithms, which means we're going to take their arguments and we're going to multiply their arguments together. That means we're going to distribute the 6 to the x minus 9, making the new logarithm's argument 6x minus 54. Okay, that takes care of the left side. We have one logarithm on the left side. The issue now is that we don't have any logarithms at all on the right side. Now, again, if you recall, yesterday we learned how you can take any number and you can disguise that number so that it looks like a logarithm. So if you have a constant, such as 4, we should be able to turn the number 4 into a logarithm. Now, we know from yesterday that technically we can pick any number that we want as the base of our logarithm and as the base in the argument, as long as we move the 4 up in the exponent on the argument. But in this case, we wouldn't just want to pick any number. We would want to make sure that the number that we chose would have the exact same base as the logarithm that's already on the left side of the equation. So I would want to make the number 4 look like a logarithm by writing it like this: log base 3 of 3 to the 4th power. That way, the two bases that are on the logs on each side match each other, because the ultimate goal is to really apply the 1-to-1 property, which would then be to cross off the log and its base only from each side of the equation. Okay? From there, you will leave behind the argument on the left side and the argument on the right side, which is 3 to the 4th power. Okay, to finish this problem off, you should reduce 3 to the 4th power so that that's 81, and this is a great example of a problem that is actually not a quadratic. You would not be running the quad program. Instead, you would finish solving this by simply moving the 54 over to the right side, dividing both sides by 6, and in the end, whatever answer you get, you would want to plug that all the way back into the original for any of the x's in the logarithms arguments to confirm that that would not cause the overall argument to be 0 or negative. Now, if that happens, that you only have one answer, you plug it back in, and it creates a logarithms argument that is 0 or negative, and you have to throw that one answer out, well, then you would say that your final answer is simply no solution. Okay. So if you look on your worksheet, you'll notice that both problems 16 and 17 are also equations, but the right side of the equation is just a number, like how this problem had just a 4. You're going to use that same strategy of turning that number into a logarithm so it matches the base of the logarithm that you're going to have on the left side. Okay. As always, if you have any questions at all, you can either email me or arrive to school early tomorrow. I will be there by 7:10, 7:15. Happy to answer any questions that you have, but the